Okay, hi everybody, welcome back. So last time we talked about drawing electric fields and how this is a tool that we can use for visualizing what's going to happen when I have charged particles moving around. And if you remember, we would draw our field lines so that the field lines were coming out from positive charges and coming into negative charges. Once I have those drawn, I can drop my test charge anywhere that I want and I can see how it's going to move because it's always going to follow those field lines. The only weird thing is, remember that the field lines show the direction that a positive charge will move. But as we know, in most cases, it's going to be the negative charges that are going to move. So you can think about it as saying, okay, if I drop an electron here, it's going to move against the arrow, whatever direction that is. Well, now, Faraday was not terribly good at math, and so he came up with this tool to help him do that. But you are good at math. So what we're going to do now is we're going to figure out how to derive the electric field for a couple of different situations. One is going to be a point charge, and then another is going to be kind of an arrangement of point charges. And we'll talk about some tips and tricks. And one of the big things we're going to talk about is what I call the 5-step procedure. And that's the procedure you want to use for solving all of these different problems that you're going to run into. It'll apply to anything that you're ever going to do. Because if you ever sat down, you looked at a problem, and you're going, oh, I don't know where to start. I don't know what to do with all this. It's really complicated. And a lot of the problems do seem to be pretty complicated, not because they're hard, but because there's a lot of little steps that have to be brought in. And so using this technique will help you organize. Instead of trying to think about the whole big problem at once, we're going to focus on individual pieces, but we're recording what we're doing as we go along. Once we've got all our pieces, then we just work it all straight back and we follow the path that we've laid out for ourselves and we'll get to the answer. You look back on that and go, wow, that was a really, really complicated problem. There's a lot of work there, and yet you knew how to do it. All right, so let's get started. Okay, so here we are at the whiteboard. What I want you to do is make sure that you've got your book open to this section here, calculating electric fields. Anytime you see this little yellow box area down here, that's a scenario. That's one problem that we're going to be solving. And you want to use this scenario solving procedure that we're going to show you here today to solve every single problem. Now, once you get out in the real world, you may feel, okay, you know what? I've got enough experience. I don't need to do all of this. But also, by the time you get out in the real world, the problems are even more complex. And so you'll find that using this technique can help you out a lot as you're trying to stay organized. All right, so with this scenario, what we want to do is we want to find the electric field due to a spherical point charge. All right, so we're going to go ahead and move that out of the way. We'll move this one out of the way temporarily. Okay, so our first step is always going to be to record our scenario. What is it that we're doing here? And so in this case, we simply want to find the electric field due to a spherical point charge. This serves as a little reminder. So when you're studying, you don't want to have to go back through and look through all of these different examples and problems and everything that you've done for this. Instead, you want some sort of a quick reference guide. And you're going to see that just being able to flip through these scenarios, you go, oh, right, here's how I need to find the E field due to a spherical point charge. Here I go. And it's going to give you the description of how to do it. All right. Our first step is always to draw a diagram. So our diagram in this case, we just want a spherical point charge. So I'll draw a circle here and maybe we'll label that capital Q. You want to put on your diagram everything that you know. Now here, I'm not given a number, but I'm looking for an expression for E that's going to depend upon Q, that's going to depend upon the charge here. So I don't want to think about that as being something that's unknown. It's going to be something that, eventually I'm going to be given because I'm going to plug this into the equation that we're going to derive. So what I will tend to do then is when we start writing down our variables here, I'll put this as unknown. I'll just put what its units are. If it's an unknown, I'll use double question marks. So for example, here I want to find the electric field. So we just use double question marks and we always put the units so that we know what units that it's looking for. So in this case, it's newtons per coulomb. All right, now I want to find the electric field. What does that mean? Well, I want to find it at some particular distance. Some particular distance, maybe r. All right, so this is our situation. Now, if I were going to draw the electric field, I'm going to draw this as though this were a positive charge. And you can tell that it's a positive charge because my arrows are going outwards. If you don't remember that, look back at the previous lesson. It might not be a positive charge. If it's a negative charge, how's it going to look? Well, those arrows are going to come inward. So our expression needs to be able to take into account whether I have a positive Q or a negative Q. But for my drawing purposes, it's okay to just pick one, and then just so that I can kind of see what's going on. So if this is my field, then I'm going to find the electric field at some distance, and we'll call that distance R, right there. All right, step 2, this is our design. Now, when you're first starting out, you may say, oh, I don't really know even how to approach it, and that's okay. As you get more experience, you're going to kind of brainstorm here how you're going to solve the problem, but you should always come back and fill that in. The reason for that is once you've found your expression and you know how to derive it, you don't want to have to go through the problem to study that because there's not much to gain by that. Instead, what we want to do is just have in words, how do I solve this problem? Okay, so let's think about what we've learned so far. We know that the electric field is the negative gradient of the potential, of the electric potential. We covered this last time. And I like to keep a little flip book where I've got just a little spiral bound set of index cards where I do nothing but write down the equation, what it's for, what all the symbols mean, and most importantly, when it applies. This particular one applies in pretty much all cases. So here's my gradient operator, which is a vector, and then my electric field, which is also a vector. Well, okay, that introduced a new symbol, and I don't know exactly what this one is. So I'm going to need to find the electric potential to get E. All right. So that's kind of my rough idea. And you can talk in equations, you can talk in words. This is really for you. This is for you to help get yourself organized. Step 3 is where we start listing all of our symbols. Well, we've already talked about a few of them. We know that the charge of the sphere, we decided we were going to call that Q. Now, this is a known, as we said. This is something, when I'm deriving an expression, this is something I'm going to already know. The E field is what's going to come out of it. So if you think of it as a machine, I'm going to put in the Q, I'm going to put in the R, I'm going to turn a crank, and the E field's going to come out. So this one is not question marks. So instead, what I do is I just put in parenthesis what its units are going to be. In this case, that's going to be coulombs. That will remind me what units it has to be when I put it into the formula. Okay, so we've also decided that we want the distance from the charge. So we'll say the distance from the sphere, and we call that R. And again, this is a known. This is something that's going to go into it. So I'm just going to put its units here in parentheses so that I remember, and that's going to be in meters, like that. The only other symbol that I've got defined here is the electric field. And we've defined the symbol E, which is a vector. Now this one, I don't know what it is. So I'm going to go ahead and mark that with double question marks, and I'll put its units. So you see, I'm just basically taking everything that's up here in step 1, and I'm kind of encoding it here. The way we know that we finished the problem is when I have the same number of equations here in step 4 as I have question marks in step 3. So don't try to think about solving the whole problem all at once. Instead, look at it piece by piece. Try to get as few double question marks as you can, because that will be the fastest way to solve it. Once you balance this, as long as you're sure that your equations here in step 4 actually apply to the situation, we'll talk about that in a minute. But once you balance this so that you have the same number of equations as you have unknowns, then you know you have finished the problem. Everything else is just math, and you're good at math. You may think you're not, but you really are. The math is actually the easy part. The hard part is getting to the math. And that's what this technique is going to help you do. All right, so right now, that's all I've got in step 3. Now, I know I'm probably going to end up putting in this electric potential, but this was me brainstorming. Maybe I'll change my mind, and that's okay. This is not like something that's set in stone. We go back and forth and back and forth. So I need to come up with an expression that will give me E. Well, let's go with our brainstorming for now. Always write down the equation as if you've written it in your flip book. We call that the shell form. So it might just say E equals negative gradient potential, done. But you should put in the symbols that you define here. And in this case, I defined it just as simply E, and that's fine. But I might call this, E1 or E2, in which case I would also want to have an E1 or an E2 over here. All right, so this is a vector, and it's equal to the negative gradient of the potential. Well, now I introduced a new symbol. And so this is how the technique flows. You find an equation that will give you what you want. If it doesn't introduce any new symbols, congratulations, you're done. You found the one that you want. In most cases, it's going to introduce some unknown symbol. So this is the electric potential. So I have a new symbol that I'm going to add in my symbol list here. So this is the electric potential. And we decided we were going to call that V. And I don't know what that is. That is a true unknown. And the units of it are volts. So now it's saying, okay, I have found an expression for E. I've got that. But now it's saying, hey, you need to also go find me an expression for V. Hopefully, I can find an expression that won't add any new symbols. If I find one that does, well, okay, that's fine, and that's going to happen. But now I'm going to need yet another equation every time I introduce a new unknown symbol. So if you look through your flip books, you're going to see that we talked about how the electric potential can be defined to be Coulomb's constant times Q divided by R. So we look through here, and did we add any new symbols? Well, we've already got the V in our symbol list. We've already got the Q and we've got the R, but we do have a new symbol, and that's K, Coulomb's constant. So we'll add that here. So Coulomb's constant is K, and that's not something you're going to memorize. You're going to look it up in your book, in your flip book, and it says 8.99 times 10 to the 9th, and the units are Newton meters squared per Coulomb squared. Just remember, these are units in the same way that newtons per Coulomb and volts are units. These are not equations that you plug something into, just like you wouldn't put kilometers into your calculator. Now, the nice thing, though, is this is not an unknown. It's something we actually know. So we've got all the symbols taken care of here. So we count. We've got 1, 2 unknowns, and I've got 1, 2 equations. I'm done. So at this point, you have solved the problem. It's just a matter of going back through and combining everything so that I can get my final answer. And the neat thing about this is this step 4 kind of becomes like a progress bar, like in Windows when it scrolls across and says you're 10% through, 50% through, 75% through, or whatever. I can use each one of these equations only once. Once I use it, I'm going to check it off and I can't use it again. When I have checked off all of my equations, I'm done. I'd better have the answer. The only thing you really need to be careful about in step 4 is making sure that these equations apply to the situation. That's the physics. The physics is not combining all this stuff and putting it in and getting an answer at the end. The physics is saying, okay, I've got all these tools in my tool belt, my flip book. Which one's going to apply to this situation? If you're doing woodworking and you've got a nail you want to put in, you're probably not going to try to put in a nail with a pair of pliers. It's the wrong tool. It's not going to work for you. Same thing here. We've had lots of equations that involve E. One example, I'll put it up here so it's not in our step. You remember that for a parallel plate capacitor, we derived this. And you may be tempted to use that. Say, well, okay, maybe I can use D as my R and all this other sort of thing. It's not going to work. The problem is that we derived that expression specifically for the parallel plate capacitor. So when I've got my 2 plates, one's charged positive, one's charged negative, that's the electric field between it, and it's constant. It's a constant and uniform throughout in between. In this case, it is definitely not the same. Remember, Faraday's rules say that the closer together these field lines are, the stronger the electric field and therefore the electric force. As I move outward, those lines actually get farther and farther apart, which tells me that the electric field, and therefore the electric force, must be getting smaller. And that's not what this one says. So just because it has the letter you need does not mean it's going to apply. So that's where your knowledge as a physicist comes in. And that's what we're trying to instill in you as a physicist or an engineer of what I need to do to think about how to get this going. All right, so let's move the page up just a little bit here. And let's start with our step 5 then. Step 5 is simply where you bring it all together. So I like to start with the equation. You can start with either equation, it doesn't matter. But I like to start with the one that's going to give me my final answer. So I'm going to say, okay, E, which is a vector, is negative gradient, also a vector, of the potential. All right, I cannot do anything with this until I get rid of this gradient operator. Now we talked about in Cartesian coordinates, the gradient operator is just partial x plus, that's a vector, partial y plus partial z. However, if you tried to use Cartesian coordinates with this situation, you're going to go crazy. Because if I want to find r, now I'm going to have to use square roots, I'm going to have to use Pythagorean theorem, and a whole lot of other things. So this is not really going to be the most efficient way. So let's get rid of that. Instead, we can still write the gradient operator in spherical coordinates. And that's going to be nice. Just to remind you how spherical coordinates work, let's say that I've got my coordinate axes here, and I've got something at some distance. The distance from the origin to here is going to be r. R hat direction is in fact a vector. It's positive as I move away from the origin. It's negative as I move towards the origin. However, r itself, the magnitude, can never be negative. I can't go past 0 in here. So negative simply means towards something that's coming in towards the center. Positive means it's moving away from the center. All right, I'm going to project this down in 3D so it kind of comes like this. See if you can visualize that. This angle here we call theta. I have defined positive here, positive theta, to be in the counterclockwise direction as I'm looking down on it. Try to visualize that. Try to think about rotating and looking down. You see that theta is going counterclockwise. You can define it any way you want. If you want it to be clockwise positive, you absolutely can do that. And there are times when that might be an advantage. The way I've drawn it here, though, that's going to be counterclockwise. And so it goes from 0 all the way around to 360 degrees, or 2 pi radians. Most of the time we're going to be working in radians with this rather than degrees, but we'll go back and forth. For this first few problems, we'll stay in degrees. So then this angle coming up from the surface up to where our r is, that's phi. And again, that's a direction here. This is a unit vector. So I have defined it as I go from the plane up. I've defined that to be positive. I could absolutely define it to be from this down to the plane to be positive. As long as you're consistent, as long as you tell everybody what you're using, you can use whatever you want, whatever's convenient for you. This is kind of more or less the standard way. You'll notice, though, that phi can only go from 0 to 90 degrees, or 0 to pi over 2 radians. The reason for that is if I tried to go a little bit further, let's do that in a different color. If I went a little bit more than that to this point, well, that's the same as starting here and just choosing a different theta. So we define our phi then, get rid of that. We define our phi then to be just from 0 to 90 degrees, or 0 to pi over 2 radians from that. All right, so that's our coordinate system. So now we need to write the gradient operator in spherical coordinates. Well, if you've never seen that before, let's change back to black. So if you haven't run into this in spherical coordinates, let's go ahead and write it out right now. So this is partial r plus, and here's where it's a little weird, 1 over r, and this is the magnitude of r, not the vector. This is actually the magnitude, because I'm going to multiply it by partial theta. So this is a vector, so I don't want to have another vector here, because then I'd have to use a dot product or a cross product or something like that. So notice that these two things are different. This is with respect to the direction. This is just the magnitude. And then over here we have 1 over r sine theta partial phi, which is also a vector from there. And again, this is r sine theta is the magnitudes. These are not vectors, these are magnitudes. So any operator I put in, any function I put in here, such as v, then just gets carried into here. Remember how partial derivatives work. If I have a v here, it's only how it depends upon r that is this term. Then here I hold r and phi constant, and I take the derivative with respect to theta, but I'm treating the other two as though they were constant. And then likewise here, I treat the r and theta as if they were constant and determine just how it varies with respect to in the phi direction. Okay, so let's go over here and let's write that out then. So that tells us that E must be negative partial V partial R plus 1 over R partial V partial theta plus 1 over R sine theta partial V partial phi. The next step then is to get rid of anything that, let's clean this up a little bit, get rid of anything that is 0 in our equation. In some cases, many cases, none of these will be 0, and I can't get rid of them at all. However, let's go ahead and look at our picture here again. Certainly, it depends upon R. We can say that for sure because, I'll fix that in a minute. We can say that for sure because as I move outward, my electric field must be changing. So this one is definitely not 0. Now, if we think about theta, that would be going around this way, kind of visualizing a sphere, going around a sphere. Do you see that at any given R, the electric field is going to be constant? So this term is going to be 0. Now, technically, that should be a minus, and that should be a minus, because that negative should carry through. But as we're going to see, that one's actually 0. Same thing for phi. If I go up around this way in this direction, no matter where I am, if I'm at a constant R, then I'm not going to get any change from this. So that one is also going to be 0. So at the end of the day, that's really nice. I'm left with the electric field is negative partial V partial R. Remember that this only applies for this specific case. That's what our scenario is for. It only applies for a spherical point charge, nothing else. Okay, so now I know that I have used, let's go back over where we can see this. I've used this equation, so I'm just going to check it off. I'm done. I need to find V. I need to find the potential. Well, that's my other equation that I have right here. Now, when I'm working with these, I draw a sidebar, and I'll write down the next equation because often I'll have to solve this equation for something. You know, maybe I need to actually solve it for R, maybe I need to solve it for Q or something like that. And so I'll do that work over here and then plug it back in over here. In this case, there's nothing that I need to do. It's already in the form that I need. So then we will take our V and we'll just plug this expression right here in for V. By the way, writing with this pen on this whiteboard is a little difficult sometimes. So if ever you're not 100% sure what the particular letter is right there or whatever, just be sure to make a discussion post and I'll be glad to explain what that is. So I've got partial R of this expression, KQ. You need to be doing this along with me. Just watching it isn't going to help you. So that's one reason why I'm not too worried about how sloppy my writing is or how hard it is to write with this online pen. But because you need to be following along. And if you don't understand what you're doing on each step, you need to stop, go back, send me in a discussion post. Let's figure out what's going on. The last thing you can do with this class is just play the video and let it go. If you do, you're not likely to be able to pass the class. So, all right, so this means I need to take the partial with respect to R. I find it easiest to go ahead and write this in this form so that I can take that derivative. And remember, even if Q depended upon time, for example, I could still pull it out because it doesn't depend upon R. So remember that the partial is just how it depends upon R is all I need to worry about. K is a true constant, so obviously I can bring that out. So I could have a K here. Even though Q may not be constant, it could be time varying, it doesn't depend upon R. So I'm going to pull that out as well. That's an important property of partial derivatives. Now when I take so that leaves me with partial R of R to the minus 1. And therefore, E must be equal to negative KQ negative 1 times R to the minus 2. So let's go ahead and simplify that just a little bit. And I'll get my final answer that E is KQ over R squared. It's very useful to go ahead and draw a box around that. Now, this is important because this R is a vector. It's in a particular direction. Now, if I had a positive Q, then this electric field will be in the positive direction. Well, that's exactly what we drew up here at the beginning. If I have a positive Q, then I know these lines need to go outward. On the other hand, if I have a negative Q, then we know that the electric field will go in the negative r hat direction. And again, that makes sense going back to our diagram. The r hat direction, remember, would be towards the center. And so therefore, it's going to be in the correct direction for that. So that's how we go about deriving something using this 5-step procedure. And the problem here was fairly straightforward. It won't always be, but the technique will always be the same. We'll always just need to go through each one of these steps, wait till I've got steps 3 and 4 balanced, when I've got the same number of equations as I have unknowns, and I'm done, and I'm ready to solve it. All right, so let's take a look at the next one. We're going to get this one out for just a minute. So here we have several, can I zoom in on that? Yeah. So here I've got an arrangement of charges. And so I've got a 20 microcoulomb charge here, a 10 microcoulomb charge here, and a 5 microcoulomb charge here. I want to find out what is the electric force at this position due to charge 1 and charge 2. Now, before we get too far into that, let's talk about that. A lot of people are going to want to put all 3 charges in and figure out the electric field due to all 3 charges. But we're considering basically charge 3 as a test charge. If I know what the electric field is due to 1 and 2, remember that the force, the electric force, which is a vector, is just Q times the electric field. So visualizing what's happening here, this Q is our Q3. Therefore, the electric field should be the electric field of 1 plus the electric field due to 2. I'm going to pause here for just a minute and talk about vectors. Now, supposedly you had vectors in the previous semester, and so hopefully you're completely comfortable with that. But I do want to remind you that if I consider the total electric field here, that is the sum of these 2 vectors. That is true. What is not true is that the magnitude of the field is equal to the sums of the magnitudes. That is not correct. Instead, I've got to actually work out the x and y components, I and j components we're going to use for this one, the I and j components for this, add up my I components, add up my j components, and that is my final total electric field. Never, never, never go straight to this. This is why we're real careful to put these vector signs on here so that we don't make that mistake. All right, let's go ahead and get rid of this. So our goal then, basically, if we're thinking about our step 2, our goal is let's figure out the electric field right here. Because going back to this equation, if I find that electric field, all I have to do is multiply by Q, and I've got the force. So that's kind of my first task. Now that leads to the next problem is, okay, well, I've got to find the electric field. Well, as we said, we've got to find the electric field due to 1. And then we'll have to find the electric field due to 2, due to charge 2. We'll add them up as vectors, and we're ready to go. So that kind of is an outline. So this might be a step 2 outline that you could do. Might be better to do it in words, or if you can remember just kind of what these are, you might say, find the electric field of 1, find the electric field of 2, and then your step 4 might be combine the vectors. So adding up their components. Anytime we're adding vectors, we're adding up their individual components. Now, I could start with this, but you see how it's at that crazy angle. Well, good engineer is a lazy engineer. So I don't want to I want to get some nice right triangles so that I don't have to worry about it. So I can rotate my coordinate system to be in any direction that I want. So why not make it so that our coordinate system, that these 2 are lying in, say, the horizontal plane? That'll make it a lot easier to visualize. It doesn't change anything. What you're actually doing is you're just saying, okay, I'm going to draw my I hat direction to be this way, and my j hat direction is going to be perpendicular to that. But a lot of students find that hard to visualize. So what we're going to do then is over here, we're going to redraw it, and we're going to draw it so that I have a bunch of charges in a line. So this is Q1, and we know that that is positive 20.0 microcoulombs. And then this is Q2, And we know that this is positive 10.0 microcoulombs. Way up here, we have, oops, let's do that with capital. And I'll go to the eraser here. There we go. So up here we've got Q3, and that's positive 5.00 microcoulombs. Let's see, we need to move that over just a little bit. Let's put Q2 right here. And you can play around with these diagrams. Never think that you're coming up with some sort of work of art. The diagram is supposed to help you. It's not supposed to be something that we could have to make sure we get all correct and straight lines and beautiful art and all that other sort of thing. It's a sketch. That's it. Nothing more. So let's go ahead and write down our distances here. We know that this is 2.00 centimeters. We know that this is 1.00 centimeters, and we know that this is 3.00 centimeters. So now I've got this in a form that's going to be a lot easier to work with. So we're going to go ahead and get rid of our original page, and we'll put this. This is now step 1. And you see how we've done that. So our scenario then is we want to find the electric force at Q3 due to Q1 and Q2. You could also generalize this and say, okay, this problem is how I find an electric field due to an arrangement of point charges. Whatever works for you. This is not something that, there's like one single correct answer for that. Instead, what you're trying to do is come up with something that's useful for you, that works with you while you're trying to study. Okay. All right. So let's go on to our step 2 here, and we'll put this down here. So step 2, we need a plan. Okay, we kind of outlined what we're going to do. So first, we're going to find the electric field of 1 at the position of Q3. And here I don't mean the charge Q3, I mean the position of the charge of Q3. Next, then, we're going to find the electric field due to 2 at Q3. Then we're going to add the vectors E1 and E2. Remember, we're going to have to add those using components. And then finally, we're going to multiply our total E field at Q3. We're going to multiply that by the value of Q3 itself, the charge, and that's going to give me the force, which is what I actually want. So that's our plan. There's a lot going on here, but each individual step is pretty easy. So break it down like this. Only focus on one step, and while the rest of it doesn't exist for you. We're just going to kind of keep that in the back of our mind. It's called compartmentalization. It's something we learned in the Navy all the time, because that gets you focused on the individual task at hand without feeling overwhelmed. And let's face it, it's pretty easy to feel overwhelmed when you're doing this. All right, so let's start with our step 3 then. We'll come back and forth to our picture here. But step 3, we want to write down all our symbols. Well, okay, we have charge 1, and we called that Q1, and we know that that is positive 20.0 microcoulombs. And you can see that right here. If you want, it is very useful to go ahead and convert these into standard SI units, into base units, because our equations require us to have coulombs, meters, newtons, kilograms, not centimeters, microcoulombs. However, if you remember your engineering prefixes, micro simply means 10 to the minus 6. So we'll say that that's equal to 20.0 times 10 to the minus 6 coulombs. And yes, I know that's not standard scientific notation, and we also don't care. This is what makes it easy for us. That micro means 10 to the minus 6. That's it. If you find yourself trying to do conversions and moving decimals around, you just added one more place that you can make a mistake. That's not worth doing. All right, so let's go to charge 2, and we call that Q2, and we said that that was positive 10.0 microcoulombs, which then is going to be positive 10.0 e to the minus 6 coulombs. You should have this on your paper where you can see this, but that's our charge right here. We just do that by referring back to the diagram. Once you've drawn your diagram, you should not have to go back to the written problem statement if your diagram is complete. That doesn't mean that there's anything wrong with going back and go, oh, wait, I forgot that, and I'll go put it back in. Perfectly okay. But you want to get to the point where you've got everything in this diagram so that you can find it. All right. We know that the charge for 3, we call that Q3, and we know that that's equal to positive 5.00 microcoulombs, which is positive 5.00 E minus 6 coulombs. Now I'm going to need my distances here, and it is okay to go ahead and start, adding these things up, but I don't right now know exactly how I'm going to use these. So I'm going to wait on them. If you want to just go ahead and record all of those, that's fine. There's nothing wrong with that. But they're here, they're in your diagram where you can see them, and they're not really unknowns. So what I want to find then is I want to find the force on Q3 due to Q1 and Q2. And we called that, let's call that F total. Give us a nice symbol, F total. And I don't know what that is. So that is going to be double question marks. And the units of that are newtons. So we're looking at our plan here. We know that we're going to want to find E1. We're going to want to find E2. So I'm going to need some symbols for that. If you didn't see that, if you didn't have a step 1 plan or step 2 plan, then just start brainstorming by writing down some equations in here. And hopefully that'll give you some ideas as to where you can go from that. But eventually we want you to get to where you can say, okay, I'm going to do this, and I'm going to do this, and I'm going to do this, and I'm going to do this. And then you've got it set up. Work with your groups. Talk to your compatriots. Get on the discussion boards and say, hey, how are you approaching this? And then go through it and see if you can figure it out. All right, so since we're going to need some symbols, we're going to do the electric field. And we'll call that at Q3 due to Q1. And so we decided we were going to call that this, and we don't know what that is. And that's in newtons per coulomb. Then I'm going to have my electric field at Q3 due to Q2. That's also a vector, and we don't know what those are. Be really careful to keep writing down these vector signs. That'll keep you from making a mistake with that. So already I've got 3 unknowns, so I know I'm going to need at least 3 equations unless some of these add new variables in here. So let's start writing down some equations. Leave yourself some space so that you can go back and add in new symbols that you add. So we've already derived the expression for the electric field due to a point charge, so there's no reason not to use that. Anything that you've derived previously, if you're sure it applies, can be used. That's why you want to have in your flipbook your results that you found. I could not, for example, use the expression for a parallel plate capacitor because I don't have one. All I've got is the charge. So when you do that, in your book, in your little flip book, you probably wrote E equals KQ over R squared. We call that the shell, but I want to use the symbols that I've defined here. So one of my equations then is going to be E1 equals KQ1 at a distance R1 to 3. So the distance from, this is an R, from point 1 to point 3. So let's go ahead and label that. I'll do that in a different color. Let's go ahead and label that here. So this is R13. That's going to help me to keep up with what's going on. Remember that the electric field is due to what's in between these two. And we're missing one term, of course. That should be R squared. Okay. Another equation we have similarly, we have E2, KQ2 over R23 squared. Now you may say, well, Dr. K, why can't I just use E equals KQ over R? I know which one to plug into that. Yeah, for a simple one you might, but as things get more complicated, it's going to be hard to keep up with that. And not only that, we can't use our little rule of same number of equations as unknowns. So you're losing some of that warm fuzzy that you're going to get to make sure that you're on the right track. All right, so let's go back and let's label that in, and we'll do that in this color. Nice little purple there. And this is R2, 3. From this one to this one. All right. Now we know that we need one more equation to get the force. So we found one equation for E1, we found one for E2. How am I going to get the force? Hopefully you're thinking about it at this point, maybe even pausing, but go through your flip book. But as we talked about, the force, and we're going to use our correct symbols here, our total force is going to be Q3 times the vector sum of E1 plus E2. Again, that's a vector sum. So just like we've got right here, according to our plan. So once I've got those, then I just multiply by Q3 and I've got it. I haven't added any new symbols here. So I have 3 unknowns, 3 equations. I'm done. There's nothing left to do but math. Now in this case, because I'm working with vectors, I've got a lot of components, there's quite a bit of math to do, but none of it is particularly hard. And if you focus on one thing at a time, you won't feel overwhelmed. So let's get started with this. Let's figure out, our plan then was to find E1 at Q3. So let's do that. We're going to need this R12. So let's define as a symbol then that we can use. So the distance from Q1 to Q3 is going to be R13, but that's not an unknown because I can go back up here and I've got a nice right triangle that I can use to figure this out. So here's one leg of the triangle is 3 centimeters, the other leg of the triangle is 3 centimeters. And if you remember from trig, that means that's a 45-degree angle, but we'll figure that out directly. Make sure that you're following here. I'm going from here to here is 2 centimeters, then another 1 centimeter, then I go up here and that's 3 centimeters. So we will go ahead and do our math here. We know that that's the square root of 3.00. Cena is e minus 2. That way you don't have to do any conversions. So 3.00 e minus 2 meters squared plus 3.00 e minus 2 meters squared. And I'll go ahead and work out that math. And so if you pull out your calculator then, you're going to get 3 squared, or 3 to the minus e to the minus 2 squared times 3 e to the minus 2 squared. Let's see if I can get a calculator to appear on screen so that we can do this together. Here we go. And let's switch to a scientific mode. Okay. Now, when we're using scientific notation, remember you always want to use on your calculator to either be EXP or EE or something like that. So never do times 10 raised to the minus 2. That'll work as long as you multiply. As soon as you divide, it's going to give you the wrong answer. So let's make sure that we're using this EXP button, or it might be like second function EE. If you can't find it, send me a picture of your calculator in discussion post and we'll figure out what's going on with that. All right, so I want 2.00 times 10 to the, and then this particular calculator doesn't have a plus minus button. Yours might. It might be like a minus sign in parentheses. It might be plus slash minus. For this particular calculator, whoops, we're going to need, oh, there it is right there. It does have it. Let's go back and do that again. So we have 2.00 times 10 to the negative 2. There we go. That's how we want it. We're going to square that. So this particular one has an x squared button. So I'll do squared plus and here I've brought our just kind of on-screen calculator. Now, when you're on your particular calculator, and all these unfortunately are going to be very different, you need to make sure that you find your scientific notation button. You will never do times 10 raised to the negative 2. That will work as long as you multiply. the first time you divide, it's going to give you the wrong answer. So we just want to get out of that habit entirely. Somewhere on your calculator is either an EXP button, like you see right here, or an EE button, and it might be second function EE if it's printed up above it. That means times 10 to the. So for this particular calculator then, we would put this in as 3.00 times 10 to the. Then look around on your calculator. Most of them will have either a plus minus or a minus sign in parenthesis. That's negative as opposed to subtract. If your calculator doesn't have that, you can try the negative button. Maybe it's set so that it can function both ways. So we don't want to subtract. We want to use the plus minus button. And then of course we decided that that was E-2. I have an x squared button on here. You probably have one on your calculator. So we'll go ahead and square that. And then we're going to add to that another 3.00 times 10 to the negative 2 squared. And we add those together and we get that this is 0.0018 meters. Whoops, that's meters squared. Yes. So the last thing we need to do then is we need to take the square root. Bring that calculator back up there. So the square root button is right here for me. And I get this big, long, crazy number. You only need to, let's put the square root back in. You only need to have that if you don't need to have all of these crazy numbers. You only need to have enough to take care of the number of significant digits you have in the problem. So we have 3 significant digits in the problem. So keep 4 numbers. Don't keep all the rest of them. They're really not doing any good and we want to be lazy. So don't write down any more of them. So this one then is going to be equal to, I keep bringing it down and forgetting what the number is. It's 0.04243. So 0.04243. 0.04243 meters. There we go. And now we're going to do the same thing. We're going to do the distance from Q2 to Q3. And going back up to our picture here, we define that to be R23. So we'll do that here. That's R23. And it's going to be set up basically the same way. We have the square root of 3 centimeters, so 3e-2 squared, plus this one right here is only 1 centimeter. So we will put in plus 1.00, again, e-2 meters squared. And we'll do just like before, we'll do this in multiple steps. So let's bring up our calculator. And we have 3.00 e to the negative 2 squared plus 1.00 e to the negative 2 squared. We hit equals, and that is square root of 0.001. So that's the square root of 0.001 meters squared. So we want to take that back then, and we will take the square root, and you see that it's 0.03162. So 0.03162. 0.03162. There we go, just like that. So now we've got our distances whenever we need them over here. All right, let's go back. Let's get started with step 5 then. So we'll start with this first one, since that was the first one in our plan. Going back to our plan up here, I'm going to find E1. So I've got what I want equal to symbols. Never plug in numbers until you have what you want equal to symbols, because there's no way you're going to go back and figure out what your mistake was if you've already plugged in these numbers. And I know students love to do that. They're like, oh, I just want to go ahead and do that so I can get that out of the way. It's not going to work for you because you're going to make a mistake at some point. And if you've already plugged in numbers, you really don't have any choice but to start over. And that is frustrating. So take my advice. Don't plug in anything until you have what you want equal to letters, equal to these symbols here. So we do in this case, so we're going to go ahead. And so I have 8.99 times 10 to the 9 Newton meters squared per, that's a square, per Coulomb squared. Put your units in here so that we can make sure that we're getting units of newtons per Coulomb by the time we're done. And then I'm going to multiply by Q1, which is positive 20.0 E minus 6 coulombs. So that means micro. And we wrote that out up here so that we wouldn't forget. And then all of that is divided by R13 squared. We've already worked out what that is, so we're going to just type in that number. And we decided that that was 0.04243. So 0.04243 meters, and then we're going to square that. All right, so let's go back over to our calculator. Let's see if I can make my whiteboard a window here instead of full screen. Nope, my word, it's not going to cooperate. That's okay. We'll just keep doing it this way. Okay, so we're going to clear this out, and we get 8.99 e to the 9 times 20.0 e to the negative sign 6 divide by 0.04243 squared equals. And that is a crazy, crazy big number, but it's actually pretty good. Now, on some calculators, you will have this F to E button. That means to put it in engineering notation. So you see when we hit that button, it automatically converts it into something that's useful for us, into scientific notation. You'll find that a very handy thing so that you don't have to count over how many zeros you have. So now you see that we have 9.987. We're going to keep 4 significant digits for now. E to the positive 7. So 9.987 e to the positive 7, and it should be newtons per Coulomb. And so you see one of my coulombs canceled, my meter squared cancels, and all I'm left is newtons per Coulomb. So it worked out. We'll do the same thing with E2. Going back to our plan is we're going to find E2 at Q3. Are you starting to see how useful having this is? Because you just can't keep up with everything you have to do in your head all at once. So it's going to be set up the same way. So we'll have 8.99 e to the 9th Newton meters squared per Coulomb. This one is positive 10.0 e to the minus 6 coulombs divided by, and here's our number up here, 0.03162. 0.03162 meters squared. All right, let's bring up the calculator then. And let's figure out what this one is. So we have 8.99 e to the 9 times 10.0 e to the negative sign 6 divide by 0.03162 squared. And again, now we've got this other great big huge number, but it's basically going to be, let's see, it was 8.99, but I don't remember what the fourth digit was. 8.992 times 10 to the minus 7, or 10 to the positive 7. 8.992 e to the positive 7 newtons per Coulomb. And you may say, hey, that one came out really close to that. Well, that's because this squared was 0.001, remember? And so that's going to cancel out here, and you're not going to be left with anything but this, and all this is going to change is just this exponent right there. So, okay, looks good. So this is my E1, and this is my E2. Notice, though, that I don't have the directions for that. So we're going to have to think of it. This is the magnitude of it. But so we're going to have to think about how we're going to get that in direction. So I'm going to get rid of my vector sign here for just a minute. But we're going to have to remember which way it is. Because if you look back to your picture, this electric field, remember, is going to be in the direction of R. So it must be in this direction right here. Let's go back to our pen. So that must be in that direction. So this must be E1. This one, on the other hand, must be in this direction. So that must be E2. So we'll figure out the directions because that's our next step. We need to take our vector sum of E1 and E2. Well, to do that, I need to know what the I hat component, I'm going to define my coordinate system so that I've got j hat positive this way and I hat positive this way. These are unit vectors. If you don't remember that, just means they have length 1. The little hat means I'm going in this direction with length 1. We tend to use I, j, and k rather than an x, y, and z because you may be using x to be a specific number, right? We don't want that to be a direction if I'm actually using it somewhere else in the problem. So we reserve I, j, and k to be that for us. All right, so I need to find the I hat component and the j hat component for the electric field due to 1. So that means I'm going to need to know what this angle is. We'll call that theta 1. So we'll go down here. And we're a little short on room here. So maybe we're going to have to just take a little blank spot. We'll do it off to the side. Okay. Let's see, let's find a clear spot. There we go. All right, so we're going to find that angle. So let's redraw it just a little bit here. We know that this is 3.00 centimeters, and we know that this is 3.00 centimeters. And this then is theta 1, and this is going to be our E1. That's our direction. You see how we've got that set up right there. So I need to know what theta 1 is. Let's move this to the side so we can kind of focus on this. Remember your trig functions? So tangent is the opposite over the adjacent. So the tangent of theta 1 is going to be the opposite, which is 3.00 centimeters over the adjacent, which is also 3.00 centimeters. Now notice that I left it as centimeters. You can convert it to meters, and maybe that's a good habit. But remember that the argument that comes out of here has to be dimensionless. These have to cancel. So it doesn't matter what units you use as long as they're the same. So you put that in your calculator, and you're going to find that the tangent theta equals 1. You're going to take the inverse tangent. And oftentimes on your calculator, that's going to look like this. I don't like this notation because -1 technically means this, and that's the cotangent. That's not correct. But you're going to find that used pretty much everywhere on calculators. So we'll go ahead and stay with that. And then if you take the inverse tangent, punch it into your calculator. On mine, I have to put in 1 and then hit inverse tangent. You may need to hit inverse tangent and then 1, but you should find that you get 45 degrees. Okay, so this angle is 45 degrees. So all I need to do then, if I want the E1 I hat component, right? So here's my hypotenuse. The I hat component is the adjacent, so that's going to be cosine. So that equals E1 cosine theta 1. And E1's j hat component, the one this way, is going to be E1 opposite over hypotenuse is going to be the sine theta 1. All right, let's go ahead and work that out right quick. We got 9.987 e to the 7 newtons per coulomb. So E1I must equal 9.987 e to the 7 newtons per coulomb times, and let's go back and check which one we have. It's going to be cosine. So cosine of 45. And then we will put that into our calculator, which hopefully I've got trig functions on this online calculator. We will see. There we go. All right, so we're going to take, let's clear, and we're going to take 9.987 times 10 to the 7 times, and then I need the cosine. Oh, I see what that's doing. Okay, nope, we don't want to do that. We have to do 45 cosine is how that works. And then we'll multiply by 9.987 times 10 to the 7. And that's our final answer. Again, on your calculator, it may be completely different. You may have to put in the number and then cosine, like I ended up having to do, or you might end up putting in cosine and then the number. And sometimes there's no way to tell other than just try it the way I did right there. So this then works out to be 7.062. So 7.062 times 10 to the 7, and it's still newtons per coulomb. This doesn't have any units, so I'm left with my newtons per coulomb. So that's my I component. My J component is going to be the same thing. It's going to be 9.987 e to the 7 newtons per coulomb, but now it's going to be times sine 45 degrees. And you should see once you plug it in, since it's a 45-degree angle, I had better get the same thing. You work it out. Convince yourself that you do. I know some of you are like, yeah, okay, I trust you. Don't trust me. I may be doing it wrong. So work it out, but with a 45-degree angle, the lengths of the legs should be the same. All right, so now I need to do the same thing for E2I hat and E2J hat. Let's go back up here where we were working before. Now my triangle looks like this. Let's see if we can make that a little cleaner. And so this is 1.00 centimeters, and this is 3.00 centimeters. This is my E2, and this is going to be a new angle theta 2. I don't recommend that you just use theta for these because it's really easy to get them confused in this area. So I need to find that angle again. So tangent of theta, it's not Q. Tangent of theta 2 is going to equal the opposite over the adjacent. So 3.00 centimeters divided by 1.00 centimeters. And again, if that bothers you, you want to just use meters all the time, I 100% support that. You would just write this as 3.00 e minus 2 meters divided by 1.00 e minus 2 meters. And you'll get the same thing. So I'm going to let you put that into your calculator. I've actually worked it out ahead of time, but you should find that you get 71.6 degrees. So take a minute and work that out. Pause the video if you need to. And then again, I've got the same thing coming back here. Once I've found that value, E2I is just going to be E2 cosine 71.6 degrees, and E2J is going to be E2 sine of, let's write that out, sine of 71.6 degrees. All right, so let's go ahead and work that out then. We decided that E2 was 8.992 e to the 7 newtons per coulomb, cosine 71.6 degrees, and our E2J was 8.992 E7 newtons per coulomb, sine 71.6 degrees. All right, going back to our online calculator then. We'll clear this out, and we've learned with this calculator we got to do the number first. We'll do 71.6 trig, and we want cosine times 8.992 times 10 to the positive 7, and that gives us 2.838. So 2.838 times 10 to the 7 newtons per coulomb. All right, let's do the same thing for the next one. We will clear that out. So I need to take the sine, so we'll do 71.6 sine times 8.992 e to the 7. And we get 8.532. 8.532 e to the 7 newtons per coulomb. So now we've got our vector components. We're ready to add them. Going back to our plan, you just add up the individual components. So I'm going to bring this over here where we can see this. Our E total, which is now a vector, I'm going to add up my I components, my I hat components. Bring that down where we can see that. And so that is 7.062 e to the 7 plus 7.0, whoops, plus 2.838 e to the 7 newtons per coulomb I hat. That's how we write that. Plus 7.062 e to the 7 plus 8.532 e to the 7 newtons per coulomb J hat. Now here I'm going to pause. You want to be real careful about the signs of these. They're not necessarily always going to be positive. Now if we go back to our picture, you can see that both of these vectors, E1 and E2, are in the positive I hat direction and the positive J hat direction. You need to set that to be what it is. The trig functions won't necessarily tell you whether it's positive or negative. Go back to your diagram and look. If I happen to be going down this way, okay, then the J hat component might have been negative. In this case, they're both positive, so we can just go with that. All right, so let's do the math. And so for the I hat component, I've got 7.062 times 10 to the 7 plus 2.838 times 10 to the 7. And so that's 9.9 times 10 to the 7. So this equals 9.9, and we still have 3 significant digits here, e to the 7 newtons per coulomb I hat. Plus, now we need to do the same thing here. And we get 7.062 e to the 7 plus 8.532 e to the 7. And we get 1.559 e to the 8. So 1.559 e to the 8 newton per coulomb J hat. Now let's think about it. Does that make sense? Is our total mostly in the J hat direction? And this is like 1, and this is like 1.5. So if we look over here, you see that we definitely have more J than we do I for E2. E1, it's about the same. So that means when I add my X components, my I components, I'm going to have less to add to the I component here. So it looks pretty good. But if you don't follow that, just work through the logic, make sure that you can see what's going on. So that is now my total electric field. Going back to our plan then, once we have our total, all we need to do is multiply by Q3, and we've got our final answer. Oops, let's put that right back where that was. Okay. So we'll take this and we'll say F total, which is a vector, is going to be Q3, which is positive 5.00 e minus 6 coulombs times 9.90 e to the 7 newtons per coulomb I hat plus a little more room. We'll also multiply Q. Now Q is a scalar, so I can multiply it through the vector here. So plus 5.00 e to the minus 6 coulombs times 1.559 e to the 8 newtons per coulomb J hat. And you see how I've done that. We know that F in general is QE. So here's my vector E. These are vectors. Q is a scalar, so I can multiply each component by Q. That's legal. So now I'll do this then, and we'll need to multiply out each piece. We'll do that together on the calculator. So I have 5.00 e to the negative sine 6 times 9.90 times 10 to the 7. And that's 4.95 times 10 to the second, which you can leave it that way, or you can just write that down as 495. The coulombs cancel. I'm left with newtons. That's good, because 4 should be in newtons. And then for the J hat component, we will have 5.00 times 10 to the minus sine 6 times 1.559 times 10 to the 8th. And that gives us, we're only going to keep 3 significant digits since this is our final answer. So that gives us 7.80 times 10 to the second. So 7.80 times 10 to the second is just 780. Again, coulombs cancel. I'm left with newtons, Newton J hat. And that is the total force. Now, this is in component form, and unless you're specifically asked for the magnitude and direction, just leave it. That's perfectly fine. That's a very valid vector. And in fact, you'll find the component form is usually more useful. As we've seen here, we've had to break it into components before we could do anything with it anyway. So don't be in a hurry to recombine that. If it does ask for the magnitude, well, that's easy. You just use Pythagorean theorem. So the magnitude of F total would simply be equal to the square root of 495 newtons squared plus 780 newtons squared. And then the direction then, let's think about this. This are both in the positive direction. So it's going to look something like this. This is our F total J hat, and this is our F total I hat. And you can see that the angle here then, we'll call that theta total, not 2, how about total, is going to be the tangent of J over I. It's going to depend which trig function you use, which one you call to be the opposite, which is going to be the adjacent. It's going to depend upon how you draw your triangle, right? Because if it's, let's say it was down this way, well, maybe we want to measure it. Maybe I wanted to measure it from here for some reason. Well, now, if this angle then, F total I hat would be the opposite, and F total J hat would be the adjacent. So it's not always going to be that theta tot equals the inverse tangent of the J hat component over the I hat component, which in this case would be 780 newtons divided by 495 newtons. It depends upon where I've decided I want to measure from. So for that reason, you have to always specify where you're measuring from. So in this case, I might say counterclockwise from the positive I hat direction. And that's unambiguous. Just giving an angle isn't enough. It doesn't tell you where to start from. It doesn't tell you, did I go here or did I go here? Because those are very different numbers, even though they're the same angle. So this is unambiguous. You could take the tangent of this, figure out that angle, and then say it is counterclockwise this way from the positive I hat axis. And that was a lot of work, but we finally got to the end. Okay, as I said, that was a lot of work. When you go back and you see everything you did, it took some time. We had to go through a whole lot of steps to get there. And that's typical. As the problems get more complex, what you want, it's okay for it to take time. What you don't want is for you to stare at it and go, I don't know how to approach it. I don't know what it is I need to be doing. So we break it into these tiny little steps, and then I do each step, and then I refer back to my plan so that I know what I want to do next. That way you're not keeping up all of it in your head and going, okay, well, wait a minute, now I'm confused and I've lost my track. And you're going to end up starting over. And then it's going to take you a lot more time than it had been if you simply followed through the steps and went with this. So even though using this 5-step procedure is optional, it is highly recommended. I've been flying spacecraft for 25 years and I still use this method. So you've got some experience here. Take advantage of it when it comes in. You'll find that overall, you're going to get things done a lot more quickly and a lot more efficiently. And then you've got this reference that you can refer back to later that's nice and organized. You don't have to sit here and go, okay, now what was I doing? How did I get that equation? Or how did I plug that number in? Especially if you just plugged in numbers and didn't write down any equations. You're not going to be able to figure out what you did. And that's not going to help you when you're trying to study for the exams. All right, we'll see you next time.